can keep this pace up. All right, thermochemistry. Types of energy, law of conservation of energy. Energy can't be created or destroyed, just changes form. Heat. Heat is going to flow, right? Heat is different than temperature. Heat is going to flow from warm objects to cooler objects. Systems, an open system, mass and energy can enter and leave. Closed system, energy can leave, mass can't. Isolated, no mass, no energy can come around. Right. So we're going to have a system, and we're going to have the surroundings, everything else, right? If I have a combustion reaction inside of my system here, how is heat going to flow? Out. How's it going to feel? It's going to feel hot, right? Because it's giving energy out. Is that endo or exo? That's exo. That means my delta H is a negative value. Endothermic, positive. So here, my system. Let's say we have an ice pack, one of those instant ice packs. We hit it, the bladder bursts, it starts getting cold. Well, what's happening is the dissolving process, there's salts in there that dissolve, is taking energy from the water that's in there, decreasing the temperature. Now, since the temperature is warmer on the outside than the inside, it's going to start to take energy in. You put it on your ankle, it's going to take energy from your ankle, it's going to feel cold to you because heat is flowing from the surroundings into that system based on that difference in temperature. So this is our enthalpy, exothermic, endothermic. We have a whole bunch of different ways that we can calculate enthalpy. Delta H of the reaction, heats of formation. So that's products minus reactants. We would have to have a list of them. Heats of formation, meaning it's formed from the elements that came by. So if we just have regular elements in their uncombined state, what's their delta H of formation? 0. Right? So we already know some of them. The other ones we'd be given, and then we can do products minus reactants to get our heat of the reaction. Sometimes it's called heat of the reaction. Sometimes they specify, instead of just the generic term reaction, they tell you the specific type of reaction. Delta H decomposition, delta H combustion. You might have COMB, combustion. Just a whole bunch of different subscripts there. That's fine. Right. Calorimetry. What's our equation for calorimetry? All right. So this, and then we have this one. Right. Same equation, just relax. All right. This one, they give you the specific heat. So this one, here the heat capacity is big C. Right. We're used to that specific heat, right? 4.184 for water, the mass of the water, the change in temp of the water. We can calculate Q. Heat capacity is figured out for a specific calorimeter. They've measured all of the they've measured all, like the walls of the container, how much energy it takes. They measure the stirrer, the thermometer, all those things. There's a set amount of water in there, and it's all packaged in for you here. One way that it's different, these two, the units. The units on C are joules per gram degrees Celsius. So then when you multiply it by the mass, the grams cancel out, times the delta T, the degrees Celsius cancels out, and we just get joules. So what is the units for our heat capacity going to be? Good, joules per degree Celsius. Why doesn't it need grams? It's all factored in, right? So when I multiply by delta T, my degrees Celsius is going to cancel out, and I'm just going to be left with joules. Is this joules, is that my enthalpy? No. But what it is, like I'll get a joules value for this. I know I'm going to have to scale it up to get the heat of the reaction. I'm going to scale it up to get what the equation actually is. If this was a combustion reaction, the combustion reaction is written as if I had 1 mole of my fuel plus oxygen getting carbon dioxide and water. I don't have 1 mole. I might only have 0.2 grams. What I'm looking for is to get kilojoules per mole, because that's how my equation is written. My equation is when 1 mole of this combusts. I only had 0.2 grams, so now I have to scale it, usually using the molar mass. Right? This will scale it up to, as if I did have 1 mole of this, what my kilojoules per mole would be. Right? I'd also have to convert from joules to kilojoules. Hess's law, we like that one. Right? Yeah. All right, so Q of the calorimeter versus Q of the reaction, or Q. So if it is a closed, isolated system, there we're going to have water probably as the surroundings, and we're going to end up whatever energy the water absorbed, that's how much energy the reaction gave off. So as the water goes up in temp, that means it's absorbing that energy. That means that's an exothermic reaction. So the heat of the water would be positive because it's getting more heat. The heat of the reaction would be negative because it's giving off more heat. And the opposite, right? If we have usually we have, we'll do like dissolve something in water and stir it, and the temperature of the water goes down. Well, that must mean if the temperature is going down from the water, that's an exothermic reaction for the water. That means our reaction must be endothermic, right? Because if the water is giving up energy, there must be the reaction occurring to take that energy. Right? If it feels cold, it's endothermic. If it feels hot, exothermic. All right. Chapter 7, Quantum Theory and Electronic Structure of Atoms. All right. Waves we're okay with. Make sure we have an idea about that order that we have, right? Visible light, really narrow band in the middle. Only a few hundred nanometers wide. Just beyond violet, ultraviolet. X-ray, gamma ray. They get more dangerous, more energy intensive, lower frequency, higher energy as we go. I'm sorry, greater frequency, lower wavelength, higher energy as we go. In this case, to the left. This way, we have just beyond red as infrared, microwaves, radio waves. Right now, those waves are getting longer, frequency decreasing, energy decreasing. These not dangerous for us, right? The stuff beyond red, stuff beyond violet, those can hurt us. Right, from a ultraviolet, from a bad sunburn. X-rays, we know we have to wear like the lead suit. Gamma rays really dangerous for us. Photoelectric effect, what's that? Right. Photoelectric effect, we shine light on a surface. And we're seeing if this energy has enough energy to knock those electrons out. Right. Here, red light, nothing happens. I can put 10 red lights on here. Nothing's going to happen because the wavelength, the energy of our wavelength of the red light isn't strong enough to knock those electrons free. Here, we have yellow light that has a higher frequency, higher energy. That has enough energy to knock out electrons. All right, I can keep going higher. Now I have blue. That ejects more electrons with even more energy from those electrons. Right. This is really a way that we can measure ionization energy. Right, we remember ionization energy required to steal an electron. That's what's happening here. Does this have enough energy to knock an electron free, to knock an electron from its orbit? If it, right, that's basically what we can think of as ionization energy, the energy required to take that away. That's photoelectric effect. Right. There's a certain threshold where it overcomes that ionization energy, and now we're able to ionize it. Right, and we're able to steal that electron away. All right. Emission spectra, ground state, excited state. This all gets into that electron configuration. We're pretty good with electron configuration, being able to use it on the periodic table, right? Ground state is everything is where we expect it to be. Excited state means an electron or two have jumped up to a higher energy level or sublevel. It doesn't have to be like an s electron going from the 2s to the 3s. It could be from the 2s to the 5F energy level. It stays there for a short amount of time, and then it falls back. When it falls back, what does it do? It has to give off energy. That could be in the form of visible light. That's where we get that emission spectrum, right? We might have, all right, we might have like a couple lines here, 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 something like this, and these correspond to different wavelengths, right? Because those correspond to particular distances going from one energy level to another. They could fall in visible light that we can see, and this is like a fingerprint for all the different elements there. Orbital notation, electron configuration, orbital. Electron configuration, something like that, right? Orbital notation, something like that, right? A couple little rules. However many orbitals there are, we have lines for those orbitals, even if they're empty, right? If this was 2, we would still draw out all 3 orbitals. One of them would be empty. Let's stick with the 3 for a second. This is helpful to us, and that now we're able to figure out how many unpaired electrons they are. Right here, how many unpaired electrons? We can see there's 3. If we just saw this, we might not think to put them out there like that. So we could see how many unpaired electrons there are. Exceptions to the orbital notation or electron configuration, there we can explain it all based on a lower energy state. It's easier to get into that configuration. We said there's a little bit of added stability to half-filled orbitals and completely filled orbitals. So when we're looking at periodic trends, there might be some inversions of, like one might be slightly higher than we expected it to, right? Based on that added stability of our half-filled versus completely filled energy levels. All right. Pauling exclusion principle, Hund's rule, off-bow principle. Those are just the rules that we use to do the electron configuration. All right. Pauling exclusion principle, we can't have 2 electrons, like both up arrows in the same orbital. We can't have something like that. Hund's rule, we got to have 1 in each one before we start to double up. Off-bow principle, we start at the lowest energy first, lowest energy in sublevel, and we fill those. So it goes 1s, 2s, 2p, 3s, 3p, 4s, like that. Right. What's paramagnetic, diamagnetic? Paramagnetic has what? Unpaired electrons. Diamagnetic, all paired, no unpaired. Who are the diamagnet? Oh, almost got it done. All right, we'll pick up here tomorrow. We'll try to record, see if this works. Oh.
Can I help you? I've never seen you like doodle stuff before.